Okay, thank you, and good afternoon to everyone. APL and Metallurgy again. I talked indeed about this last year in the user meeting. Last year I had just started working for Dyalog, less than a month, so mostly I talk about good intentions and plans, but today I actually have some results. So just to refresh your memory, the idea here was to put APL back into academia. We think that it can be the right tool for scientific research. And the way we are doing it is I'm working together with Ghent University. I work in the field of material science, mechanical engineering, so metallurgy. And the idea is that I use it for my own research as an example, and also I try to teach it to everyone who is willing to listen. We made a plan. You know, you don't always follow plans perfectly, but more or less we keep the goals. Some tasks become a bit longer, some tasks become a bit shorter, but more or less we follow the plan. So I'm going to use this as a template to talk about my results. Mostly what I have done is to write a lot of APL code and try to show it to people. But I'm a scientist, so the first thing we do is to evaluate the state of the art and check the scientific literature. So that's what I did, and there are not many papers talking about the use of software in science, but there are a few of them. You have some samples here. And I want to put some quotes that I find very interesting from these papers. And mostly what they say is that in scientific computing, something particular is that the scientist is the developer. We are working in problems that don't have a solution yet, so you cannot give a specification to some software developer so that he does it for you. And the scientists are trying to solve their own problems. They are not software developers, so they don't follow the typical software engineering traditions, and they do things in their own way. And you need a lot of experimentation to write this kind of software. And domain experts and playing with code, so on. As you can see, all this will fit very well with APL. It matches very well with the typical pitch of APL, but none of these papers even mention APL at all. I think that's unfortunate, even more than unfortunate, it's plain wrong. And I'm very glad that Dyalog wants to fix that and do something about it. I would also like to add something from my own experience. As I said, I try to talk about APL to everyone I find. And well, they have never heard about it. Think also that I'm talking about mechanical engineers and so on. But they don't know what APL is at all. At the beginning, they feel a bit overwhelmed. You know, the symbols, they see that, they think it looks very difficult. But then they ask you what they can do with it. How does it compare with the tool that they are actually using? In fact, what they want to know is, can APL solve my problem? And well, that's where we are now, and then I will show what we are doing to try to fix this. So development, I'm calling this development because I'm writing some code, but mostly what I'm doing is writing tutorials. The first one I wrote was an introduction tutorial to APL. There are already a few of them, and some of them are excellent. But I needed something that I could use to teach some students very fast some APL so that I can move to some more complex topic. And then I wrote one where it's divided in 3 parts. And what I say is that in the first part, they learn to use APL like a calculator. I don't use arrays at all, but then they can learn the syntax, they can learn to write functions, they can learn about the operators, and so on. And then in the second part, I tell them that they learn to use APL like in a spreadsheet, like they will do with Excel. And there I introduced the arrays, all the mix operations, and so on. And finally, in the third part is what I call actually programming. And there I talk about all these tools, how to read files, how to write them, and so on. The tutorial doesn't assume any previous knowledge about programming. So I start very basic. This is basically the beginning, which is something that you can show to anyone and they will understand. And then they have their foot there and they know that they can move forward. Yeah, I explain a little bit how the syntax work, the primitives, so on. I talk a little bit about the system and about thread fonts and so on, but just so that they know that it exists. I don't really get into that too much. And actually, all the samples are really simple. So they don't learn to write real applications with this. But it gives them something to begin with so that we can move to some real topic. I have this both in a presentation as a Jupyter notebook so that they can follow it on their own, or I can show it in a lecture or something like that. Then after teaching them this, I moved to more specialized tutorials, and I have written a few of them that could be useful mostly to any engineer. One of them is about plotting with sharp plot, for example. Also how to do some linear fitting. This is very easy to do with the domino symbol, but it's good to show them some examples of that. Some simple calculus, just calculating numerically some derivatives, some integrals, and so on. I have one about geometric algebra. I will talk about this a little bit later. And something in which I'm working now is a compendium of formulas that everybody can understand. And I think that this helps you to get familiar with APL. For example, you will never write a function to calculate the area of a rectangle. That's not needed at all. But I think that when you see together the rectangular area formula and the square area formula with the selfie, you actually memorize it, at least if you have some visual memory. And yeah, I'm also adding here typical formulas that you see in your physics course. For example, the uniform acceleration formula, you would express it in APL. And yeah, you can imagine I have the gravitation formula, the diffusion equation, these kinds of things that most people know. And I just show how to write it in APL. And well, this would be in general for engineers, but then I have some tutorials specifically for material scientists and engineers. One is about the analysis of tensile experiments. This is just an example of how to analyze experimental data. So I show how to read the files, how to do the plots. You have to do some cleaning in that data and so on. You get different graphs. And you get different results from there. Also, this is both a Jupyter notebook and a presentation that I can show to people. Another tutorial is about crystallographic orientations. This is an interesting topic. I will explain a little bit what it is about. When we talk about the orientations of crystal, we represent the orientation as three consecutive rotations around different axes. And then you are given that, and what we want to do with that is to calculate misorientations between different crystals. We want to know how much you need to rotate one crystal to get to the position of the other one. The problem here is that we have symmetries. I want you to think for a second about a Rubik cube. And if you have a Rubik cube like that, you could apply to it different rotations. Here you apply 19 degrees rotations, and you have 24 different ways in which to put the cube. But if you have what we call cubic symmetry, all these positions are the same. And then the problem is that to calculate the misorientations, you need to calculate 24 different misorientations and then choose the minimum one. We want to do this with experimental data. This is the typical result from an experiment in the electron microscope. That's a sample, a very small part. You can see the scale bar, that's 25 micrometers. And it's different color indicates a different orientation. What we want to do is to calculate all the possible misorientations between all the orientations we have there. Normally we have several thousands, maybe millions of misorientations. So you can imagine that just calculating a cross product with a million of orientations, the other million, and then 24 times for each of them, this is a challenging problem that requires some thought. While I'm still working on it, the code I have works well for relatively small things, and I'm doing some tests and so on, but you really need to go parallel here to do this effectively, and that's what I'm working in now. And another problem I told the students about is grain growth. Probably you are not familiar with this at all. The materials, polycrystalline materials, metals in general, they are divided in grains, in portions of materials with different orientations. And when we apply some heat, these grains will grow, trying to reach a state of minimum energy. This could look a bit complicated, but you see this every day, the same thing that happens with soap bubbles. If you have bubbles and you look at them, and you can do this in the bathroom, then you see that they merge and they become larger bubbles, and eventually the boundaries between the bubbles disappear. And this is the same process that takes place in metals. Well, I explained to the students how to write a model to simulate this, a relatively simple model, something that we could say is textbook material. So they have to calculate different energies for the grains, for the boundaries between the grains. And we do all this in APL. And I'm also using Python to represent the results, and we get some results like that. I will not get too much into this because I'm going to talk about it tomorrow. So if you want to know more about it, come tomorrow to my other talk. And then I'm using it also for my own research, for more advanced topics, let's say. I'm going to talk a little bit about geometric algebra now. Geometric algebra is a way to represent different geometric entities. Normally we use vectors, vector analysis, and vectors are 1D. In geometric algebra, you also have 2D objects, which are planes. We have 3D objects, which are volumes, and we can even go to higher and higher dimensions. I put this in research because in what I'm basing this is actually some research material. It's still, it's not very well established yet. And I think it's also interesting from the APL point of view. I'm going to show an example. This is my geometric product function or operator. I won't get into the code, but I'm going to show an example with complex numbers. Complex numbers can be represented in geometric algebra too, and I think all of you will understand complex numbers. So at the top, you have the normal multiplication of complex numbers. In my geometric algebra, let's say library, what I do is I represent the complex numbers as a vector with 2 components. But what I like about the complex product operator is that if you have several complex numbers, you can have the real components in one column and the imaginary components in another column. And then you will get the same result as using the typical complex numbers. And what I'm really proud of is that you can also do this with the cross product or the inner product. And having the same operator, we can also do cross product and inner product operations. This is an example with complex numbers. Complex numbers are fast if you do it in the computer directly. But if I want to calculate misorientations, for example, and I have millions of them, you really want to have your data in columns. You don't want to do the operations one by one for each of them. And this is a quite effective way to do it. So we can do it not only with complex numbers, it also works with vectors, b-vectors, trivectors, and well, in fact, with anything that can be represented by geometric algebra, which includes also quaternions, octonions, hyperbolic numbers, and a number of different things that we normally use in maths. Then grain growth, again, here, as I said, the model I'm showing to the students is textbook material, but we are also working in a more advanced model. In the one I showed to the students, they don't really use the orientations. We use some fake orientations so that they don't need to do all these operations or all these calculations for the misorientations. But in this one, I'm actually using this Euler namespace that I showed before to calculate them. I also have another namespace to work with VBSD data. That experiment I showed before is CBSD data. That's the kind of experiment that we use. Yeah, like this. And well, we are trying to improve the grain growth model itself. We are adding the concept of time, of boundary velocity, and so on. It's a bit more complicated, but we are working on it. I'm working on it together with more people at Ghent University. They do the experiments, they test the models, and I basically write them. And the last topic I would like to talk about is crystal plasticity. This is a topic that I really like. It was the topic of my thesis. In crystal plasticity, what we do is to simulate the deformation of materials. Here, for example, we have a very small region of material, and we represent the different grains in a finite element grid. But here you have a very, very small portion, and normally we want to do simulations with structures, something like that. So what you can do is, from here, you calculate the texture. This is just a weird way to represent the distribution of orientations in the material. And from something like that, you can calculate the constitutive curve, and you use that in another model, in another simulation, where you have the actual part that you want to work about, and well, that will correspond with someone in reality. Normally, when you work in this field, you do simulations, you have to choose what you want to do. You can go to the very small, to the micro scale, or you can go to the macro scale, but you have to choose. And I think I found a way to move between one and the other. I'm calling it CPFEH, which is a mouthful. It stands for Crystal Plasticity Finite Element Homogenization. And I think I already have the theory figured out. It's relatively simple because it's based on a basic principle, which is the superposition principle. But I'm still working in the code. I think I know how to do it, but I have to write the APL yet. And this is one of the things that I will do next. And then to finish, another task that I have was dissemination and promotion of APL at the university, at academy. Mostly I have worked with Ghent University. There I have given several talks, some introductions to APL. I have also shown how to do the analysis of tensile tests that I saw before, and so on. And last semester I was also teaching the course on computational materials. And there the students they themselves work in a grain growth model. And this is mostly what I will talk about in my talk today, about how the students do it and how I think they could do it much better with APL. Recently, I have also been visiting Jötbold Loránd University in Hungary. Here, the Faculty of Informatics is a very applied faculty. It's called the Faculty of Informatics, but mostly they are not computer scientists. They are people working in bioinformatics, geoinformatics, computational materials, and so on. In the faculty, I gave a couple of talks in general about APL, about the history of APL, about how we use APL today, all the tools we have, parallel execution, these things we didn't have before. And I also gave 2 talks to material scientists. This was quite interesting because I showed the introduction tutorial and the grain growth tutorial, and it was everything in the same day. They had never seen APL, and the comparison I told to the students was it's a bit the same as if you don't know English at all, and in the morning you go through the English dictionary very fast, and in the afternoon you try to read Harry Potter. And the idea is not that they understand everything about Harry Potter, it's that they get interested enough to actually learn English and read all the other books that there are about Harry Potter. And well, the students manage surprisingly well. They can get APL in the morning. So there's something I was very happy about. I was very surprised. So yeah, for the moment I have worked with these 2 universities. I'm in talks with many more people. Some of these things will work, some of them won't, but I hope to keep spreading the word, let's say. And yeah, to finish, we think that APL is a very good choice for scientific research. We are totally sure of that. It's not always so easy to convince other people. Normally, it's easier to convince the students than to convince their promoters. But well, we think there is potential, and we will keep trying. And yeah, we have some plans for the future. I have received some feedback after doing all these things, and I will apply that. Also, if you have any comment or anything, please tell me. I will keep writing more tutorials. I will publish them somewhere. For the moment, they are not. I'm testing it before deploying, let's say. And I will continue my research. I will continue working in all these things. I hope to publish some papers and also some testing packages. And yeah, keep working also with more universities and so on. And that's all. Thank you.